Okay, on this problem from exam number 4, you have to identify the diatomic element whose root mean square velocity is most likely to be 217.723 meters per second at a temperature of 25 degrees Celsius. So you're going to use your root mean square velocity equation rearranged to solve for molar mass, and you should be able to determine which element it is based on that, or at least get close enough to pick one of these 7 diatomic elements. So first thing, I just go to my reference materials and I pull out some information. When I'm doing this root mean square velocity kind of problem, the R value that I use is given as 8.3145 kilogram meter squared per Kelvin mole second squared. So that's ultimately going to return me a molar mass in kilograms per mole. Then I'll just do a simple conversion to get it to grams per mole and then work from there. So through substitution, converting my 25 degrees Celsius to 298.15 Kelvin and squaring the velocity right here, I can work the math out this way. And this becomes my molar mass in kilograms per mole. Then I convert to grams per mole just simply by 1 kilogram is 1,000 grams, multiplying by 1,000, and I get 156.89 grams per mole. Excuse me. And then remember that it's diatomic, so that means there's 2 identical atoms that go to make that. So I need to divide that in half. So I get about 78.443 grams per mole. And I go look at all my diatomic elements, and the closest average atomic mass to that 78 is bromine. So I'm going to choose bromine as the most likely diatomic element to be in that situation. Then the next one that I'll do, what mass in milligrams of nitrogen gas occupies a volume of 300 milliliters at 125.55 degrees Celsius and a pressure of 21.25 psi. And then I instruct you to round your answer to 2 decimal places at the end of your calculation. So we have a pressure and a volume and a temperature. What mass? We could get the ideal gas law and solve it for moles, and then convert moles of nitrogen gas to grams and then grams to milligrams. So I'll use the ideal gas law and solve for N, the number of moles, and then that number of moles, then I'll convert to grams. So I substitute and change my volume to liters, my temperature to Kelvin. I use the R value for PSI, so I have liter PSI per mole Kelvin as my unit for my R, and that just comes from my reference materials. And whatever I get gets multiplied by N2's mass, which is double that of nitrogen, and then that'll be grams. And then there's 1,000 milligrams in a gram, or 1 milligram is 10 to the minus 3 grams. So then I would just either multiply by 1,000, how you set it up, or divide by 10 to the minus 3. That way, and that's a straightforward shot to get into your answer in milligrams, and to 2 decimal places, 371.44 milligrams of N2. And on this problem, you have at 5 degrees Celsius in a 12-liter container. You have this mixture of gases, and what is it? You want to find out what the pressure of each gas is in the unit requested, and the total pressure in psi. So that was this question here. Using the ideal gas law, I can use each one of these solving for N to get the number of moles, and then substitute that into the equation solving for pressure, and use the R value that goes with the unit that is in each particular situation. So the 278.15 Kelvin is 5 degrees Celsius plus 273.15. and the volume of 12 liters. So that'll stay the same for each calculation. And then the next thing, once you solve this and you get them in their individual units, like here I solved for helium pressure in atmospheres, I went ahead and converted that to PSI. So it would be straightforward when I went to add it up to get this final total pressure. So for the helium, 0.467 atmospheres, and you need to, like for your calculation for each thing that you use, like for example the atmospheres to PSI, you need to use the back cover of your book reference material, where it has like 1 atmosphere is like 14.70 psi. So that back cover of the book, for each individual 14.70 psi, there's a conversion for bar or millimeters of mercury or whatever, where it's got standard atmospheric pressure. So that conversion, I use that. So basically 0.467 times 14.70 divided by 1 gave me the PSI for atmospheres. And then the next part right here, the neon came out to be approximately 400 millimeters of mercury or 7.73 psi. And then on the bar, 1.943 bar, 28.19 psi. And then you add those together and your total pressure, 42.78 psi. Once you converted them all to psi and added them, the same like units, you should come out to something like that, I believe, if my calculations are correct.